This section focuses on the analysis of a sloped bar. Next, we are considering the total length of a bar with varying cross-sectional area as shown in the illustration. Let's say that a plate of the thickness h and the width of the left side b1 and the right side b2 is in tension. There is a load P acting like this on both ends. The width is given as Bx. Once getting the width, we can calculate the cross-section area as the product of the thickness and the width. Then, the stress is the load P divided by the cross-section area. As in the previous problem, the stresses should act uniformly in the width direction of the plate, as shown in the illustration. As for the end of the bar, the illustration shows the load acting on the middle. However, in reality, the stress is acting uniformly on the width direction. In this case, we can consider in the procedure of the following. The cross-section area is a function of the coordinates, taking the coordinates in the longitudinal direction of the bar. We are considering that the cross-section area is not uniform due to the slope. Then, calculating the stress, strain, and total elongation. Now, let's start with the width Bx. We define the width as a function of the coordinate x. As you saw in the previous illustration, this is a linear function. So, we can approximate a linear function where b1 at x equal to 0 and b2 at x equal 0. Now, we have a linear function of a line such that the y-intercept is b1 and the slope is b2 minus b1 divided by L as the equation. We firstly get the stress, dividing the load by the cross-section area. We divide the stress that has come out by the Young modulus to calculate the strain. This is a procedure to get strain in this problem. We should be noted that both stress and strain are given as a function of x, the longitudinal coordinates of the bar. So, the total elongation can be calculated by integrating this strain in the fraction of dx. To understand this integration, you need to be clear that this argument firstly focusing on the rate of elongation at this fraction. The small deformation can be calculated by epsilon x multiplied by dx. Also, note that the integral means the sum of them. It may be easier to understand total elongation is the sum of elongation of each of the fractions of dx. It is a calculation similar to the integration of velocity to get total displacement. We integrate this fraction in the bar to get the answer. We integrate epsilon x, the rate of elongation or strain at x, which is a function of x, from 0 to L to get the total elongation. The answer, the total elongation of the bar, includes a form of log